Morning, everybody. Good morning. Sorry for the late start, but my tech didn't want to work this morning, and I've had to go to an alternate program. So hopefully the recording works. We'll see. Let's see. Tomorrow is lab number 7. Centripetal motion. Right? You have that lab packet? Pretty sure you do. What if instead, during lab, I gave you time to work on your homework? I'm going to call an audible here. Lab 7's okay. It's okay. But I'm not sure it's the concept and ideas you need reinforced right now. And I'd rather you get help on your homework and all that kind of stuff, right? So come to lab tomorrow ready to do homework. Whatever homework questions you have, it'll kind of be like GRASP, right? I won't have anything to present, all that kind of stuff. Why don't we do that tomorrow? Does that sound good? Okay. Yeah, I think, we got the test next week. We want to get ahead of these things. It's easy to forget Newton's laws when you've got to deal with energy, all that kind of stuff. So let's do that. So that'll be tomorrow. Friday's GRASP. Monday is more lecture. I think there'll still be more time to do homework help there. And then Wednesday we'll review. Just get all the final questions answered, all that kind of stuff, and then take the test. That sound all right? Okay. Do I need to talk to any of your other teachers about exams that you have? Tell the other teachers to back off, any of that kind of stuff? Yeah? Some of you are like, yes, Mr. Babe, let's do that. I mean, I can talk to them, but it's probably not going to change anything. It's the way it works. All right. And you guys know why all your exams always seem to be at the same time, right? It's because we sit down and plan it that way. Oh, yeah, no, we sit there and we say, okay, we have Emma in our classes, so how can we make Emma's life as just as bad as possible, right? Ramsey, we don't like Ramsey, so we're going to make sure that we put all of Ramsey. No, it's science books tend to have units or ideas put together that are broken up into 3 or 4 chapters. This happens in chemistry, it happens in physics, it happens in biology, and it's just kind of a natural thing in STEM to be having an exam every 3 to 4 chapters worth of material. Some teachers push it to 6, but it's just got this natural flow to it. And it gets worse because when you get into junior and senior level, you'll have basically a midterm and a final, and that will determine your grade instead of having like 4 exams or something, right? In which case everybody has a test like right in the middle of the semester. It's called midterms for a reason. And it gets bad. All right, let's do this. So what I want you to do right now is turn to each other and set this one up together. Right? I want you drawing picture together. I want you discussing where the initial goes, where the final goes, where you're going to put 0. I want to give you a good 5 minutes to really try to get this one started, because I know a lot of you have trouble just sort of getting started with an idea. So this should be, within the next minute or so, should be a pretty noisy affair, right? As you compare drawings, discuss where you're going to put initial and final, and if you're even that far ahead, start writing down the conservation equation. So go ahead and do that. Call me over if you're getting stuck, if the people around you aren't getting any traction. Excuse me.
jumps out of the plane, should we assume his initial velocity is 0?
Yeah, right. When we're not told otherwise, just assume it's 0.
Mr. Balogh, what's the retarding force and the
Like air friction.
air friction?
Yeah, right?
Alright. Is that like a mu or something? Should I write it?
No, it's a force, right? It's measured in Newton.
The total force, yeah, total force.
Is this what it looks like in the back of the bus?
Yeah.
Yeah?
Yeah. Pretty cool back here, right?
Is it? Yeah. You can always tell if I'm interested in something, I'll sit in the front. But if I'm not interested in something, I'll sit in the back. That's kind of how I roll. So basically, most meetings at this campus, I'm sitting in the back. How are we doing? What are you getting like stuck on? Like what's causing difficulty or? Oh yeah, right. Like what's? Right. Like when they jump out of the plane, is the kinetic energy? What's going to happen to kinetic energy? It's going to increase, isn't it? But when they open the parachute, what's going to happen to it? It's going to decrease, right? And then they're going to hit the ground. So like, right? The answer is no. Because does delta kinetic energy show up in the work conservation equation? I mean, technically it does. I'm going to show you something real quick. You don't have to write this down. I just want to point this out, right? Work other plus energy initial equals energy final. Okay, this could be kinetic energy initial and potential energy initial, right? And then this could be kinetic energy final plus potential energy final. Okay, I'm going to rearrange. I'm just going to move I'm going to move these initials over to this side. What's this? What's this? So Elijah, there's the answer to your question. The change in kinetic energy is in this statement up here. Okay? Now, some books teach it with this box right here. Okay? I personally have found that this is harder to understand, more esoteric, and harder to apply for somebody who's kind of new, especially if you've been through high school physics where they probably taught energy start with equals energy you end with, right? And this version feels more familiar. But it knows about all of these changes that are taking place. So you don't need to focus on the changes. What do we focus on? What we start with, what we end with, and any other thing we can't figure out, right? And a lot of you are like, well, Mr. Balogh, that's everything in the problem, right? So what did your picture look like? Did you have like a... Okay, so you had a guy in the air, or a gal, doesn't matter, right? Leaving the airplane. And then they're falling, and then something happens. What happens? Parachute opens, right? So they tell me, so we know that they opened, was it 200 meters above the ground? Okay. So where did they leave? 1,000 meters. So this distance is 200. What's this distance? 800. All right. So, what's different?
Well, it's free fall, it's 50 newtons.
Oh, okay, so there's an upwards force of 50 newtons, and it's not really free fall, right? Because we've got air resistance now, right? Okay. But we know on average, right, the resistance here is about 50 newtons. So the problem tells us, right? And then after the parachute opens, the force is what? 3,600 newtons. How do we deal with that? Okay, so I could write down some other information here. What's the speed up here, like the initial speed? 0. They don't say to consider like them jumping out as moving or anything like that. And then we know something about how fast they're... Oh, no, we don't know. We want to know V final, right? We want to know how fast the skydiver hits the ground. So that's kind of... And did we know anything else? I think I kind of got all the numbers that they... Oh, the mass. We know the mass. Okay, great. All right. Strike. Yeah, Lewis. Okay, like change in this upwards pointing force kind of thing? I don't know. Wait, I'm lying. I do know. But like, I'm trying to put myself in your shoes, right? You've got this question. You're like, what do I do with this force, right? Let's strike out for safety. You're drowning right now, right? You don't know how to set up the problem. Push towards the methods that I've been trying to teach you, right? And the method is what? What do we do next? We write down this equation and we start thinking about it, right? We start using the concept of conservation of energy, and that could inform us to go back and fix our diagram or something, right? It should be what we call an iterative process where you're going back and forth and all that kind of stuff. Okay, so we're going to start with work other, and you've noticed that I tend to do work other last. I try to figure out my energy stuff first, and then I go back and see if there's anything I haven't taken care of. So initially, what kind of energy? Oh, wait, we can't talk. Why can't we even talk about initially? What have I failed to do? Oh, I didn't pick an initial and a final and a 0. Notice how going towards the tool prompted my brain to go, wait, what does initial mean? Like, where isn't it, right? And, oh, I forgot to do that with my drawing, right? So we've got to pick an initial and a final. Well, where's the final going to be? Yeah, down here at the ground, right? That's where we're trying to find something, so we might as well put final there. Okay. So where are we going to put initial? Oh, okay. Wait. Don't I have to wait a second. Oh, okay, you want to put 0 down here too? Okay. So what about the 200? We did a water problem, right? And do you remember what I said about the water problem? Or like, you kind of have to believe and have faith that what? That it'll work out. Pun intended. That was good. I liked it. that if you go from an initial point to a final point, that energy can work out everything that's happening in between. We just have to kind of be clever about how we feed it information, right? But we pick an initial, we pick a final, we try it out. If it doesn't work, we try something else, right? We have the courage to be wrong. All right. So, okay, so now I have initial, final, and a 0 point for gravity. Are there any springs in this problem? Thank goodness. Okay. So, initially, up there at the top, we say that they're not moving. So there's no kinetic. Is there any potential energy up there? Yeah. Okay. So we do know that there's potential energy initial, right? Okay. And then a final down here. Okay. Any kinetic energy down here? Yes. So we're not saying they're coming to a stop when they hit the ground, right? We want to find out how fast they're going when they get to the ground, right? So they need to have some kind of kinetic energy in order to have speed. So we're going to assume, yes, definitely, kinetic energy. Okay. Now what about gravitational potential energy down here? No, we're at 0, or really, about to reach 0, right? So no potential energy down there. Okay. And then there's some kind of work other. All right. So we've identified the kinds of energy we need. And what do you want to do? Do you want to tackle work other, or do you want to write down the math for the potential energy and the kinetic energy?
Let's do work other first.
Work other? Okay, why not? So we've taken care of gravity, right? It's in the potential energy initial, right? What have we not taken care of? What other forces are there that we have not taken care of? Air friction. The 50 newtons we haven't dealt with, right? And the 3,600 newtons we haven't dealt with. How many forces are doing work other? How many forces do we have that aren't gravity? 2. So work other is going to have 2 terms, 2 elements, 2 parts. These work other, energy initial, and energy final, you can think of them as sums, right? We're adding up all the work others. We're adding up all the initial energies. We're adding up all the final energies. There are these baskets that contain these things. So what work does the 50 Newton force do? Well, okay. You said negative work. Why was it negative work? I like all of those ideas, but there's a simpler way to look at it. The parachute is going down, and what direction is the force acting? Up. Negative, right? So it'll be 50, I'll just, symbols. I'll call it F1 times D1. Okay, we know what those numbers are, right? What's D1? It's 800, isn't it? Right? What's force 1? 50. Okay. And then the work down here? Positive or negative? Still negative. Opposite force to, right? And then it's going to be F2 times D2. And what's F2? 3,600. What's D2? 200. Okay. So when I go to write work other, both of these things have to go into it. I've got 2 different forces doing 2 different amounts of work. I got to add up all this other work that's taking place in the problem. So this will be negative F1 D1 plus a negative F2 D2. Notice, see how I'm adding them together even though they're both negative? I'll come up with a bigger negative number, but it's the sum of the works. Okay. And then potential energy initial. It's going to be mg, what y? Yeah, it's like, I'll say h, right? Where h is this total, it's the 1,000, isn't it? Okay. And that can be kind of tricky, right? To get the right height in there. You've got to realize that this potential energy initial is defined from where we said 0 was. And how far from 0 to the initial point? It's 1,000 meters, right? So that's the number we got to put in there. All right, and then kinetic energy final, mathematically, looks like what? Looks like that, right? Let's see, do I have, I got numbers on this one, don't I? Not on that part of my notes. And there's skydiver. Okay, so what do we got going here? We got to throw in a bunch of numbers and then solve for V, right? Negative 50 times 800 plus a negative 3,600 times 200 plus 80 times 9.8 times 1,000 equals 0.5 times 80 times V squared. So I've got a bunch of numbers everywhere and a V that I have to solve with. I'm going to end up with a square root, right? And they just want speed, so it doesn't matter if it's plus or minus. And you can put this all into the calculator or Wurzel, whatever, right? And this is what I got. Luckily, I did not get a imaginary number, which means this is real stuff still. Anybody want to guess? Like how fast they're going? Oh, did you figure it out?
I did it. I don't know if I'm right because it says he's going 25 meters a second, which means he's cooked.
24.5 meters per second is what I got. That's approximately 55 miles an hour. Hitting the ground at 55 miles an hour. Is that a good day? That is not a good day. It's just not a good day, right? So, yeah, okay. So what does part B ask us to do? Okay, so now, so it's a slightly different take on the problem, isn't it? For part B, we want V final to be equal to 5. What do we not know? Okay, is this height going to be higher or lower than 200 meters? We know it's got to be higher, right? We need the parachute. Parachute needs more time, right, to do its thing. So we know it's going to be up here somewhere. But so that means that we don't know D2, right? And we don't know D1 either. All right, well, do I have to start the problem all over again? Can I recycle this right here?
Yes.
Is all of this still true? Yeah, I just don't, instead of being able to put in numbers for D1 and D2, right? Those are unknown things, aren't they? So I can, nothing's really changed in my set. Has my initial point changed? Has my final point changed? Has my work other changed? Well, I mean, yes, the distance is right, but like the setup of it hasn't changed. So I can go back, I can recycle, same concepts, everything goes right there. It's just now, when I put in numbers, I'm going to get negative, 50 D1 plus a negative 3,600 D2 plus mg, I could put in numbers, Mr. Bailey, you're doing numbers today. 80 times 9.8, is this still 1,000? Yeah, okay. Equals 0.5 times 80 times 25. How did I get 25? 5 squared. Okay, so I don't like this. Because there's 2 unknowns here, isn't there? Yeah. Yeah, okay, so we have 2 unknowns in one equation. What's the other equation, Liam?
The other equation is D1 is equal to, D1 plus D2 equals the total height.
Right? We do know that whatever D1 and D2 are, Okay. For example, what if we had to open at 300 meters? Okay. What would D1 automatically become? 700, right? We know that whatever this height is, if you add the two heights together, you got to get 1,000. Can't have more, can't have less. So there's really our second question or second equation relationship that we need. Be able to tease this out. Since we're solving for D2, like we want to know how high above the ground, I would solve this for D1. Right? And now this gets plugged in right there. And what do you have left? How many unknowns now? Just one, yeah.
In our new equation, shouldn't we have 5 for the velocity?
It's 20. It's 5 squared.
Oh, okay.
V squared, right? I did that in my head because squared scare me. All right. Does anybody want to guess? Oh, Emma.
I just have a quick question.
Please.
Where did the 1/2 mv squared come from again?
1/2 mv squared was the kinetic energy at the final point.
That's just what it is.
The equation for kinetic energy is 1/2 mv squared. Yeah. Yeah. All right. Anybody want to guess as to what the actual height is? Liam, you know it? Okay, hold on a second. So like 300, 400, any guesses? 400? Liam, what is it?
I got 206.5 meters.
206.5. A 6 meter difference. Just 6 meters. Why was it just 6 meters? How big a force is that parachute compared to the air resistance on the way down? It's really big. What is a parachute's job? To increase the air friction, right? It increases the air friction so that the acceleration, right, change in velocity gets you to a point where you're not going to die when you hit the ground. Why would anybody jump out of a plane and then open their parachute so close to the ground? I mean, that's dumb. So I actually went skydiving this summer. It's first time and probably last time I'll ever do it in my life. It hurt my back. That's why it's the last time. So, I mean, my back was already injured, but it just made it hurt more, temporarily. My father-in-law was turning 80 years old, and he wanted to jump out of an airplane. So I went jumping out of an airplane with him. I felt stupid because I didn't so one of the things that I asked my instructor, I said, so I'm kind of worried about the whole jump out of the plane and like my stomach, like, staying behind in the plane and that, that feeling you get when you're just falling. And he said, that's not going to happen. I was like, but we are jumping out of an airplane. He's like, yeah, the airplane is moving at 100 miles an hour. And we're going to go to 120 miles an hour as our fastest terminal velocity. What does your stomach feel like when you are accelerating from 0 to 20 miles an hour in your car? I was like, doesn't feel like anything. He's like, that's what's going to happen. It hadn't occurred to me. Stupid physicist, right? Hadn't occurred to me to add the velocity. I was assuming like drop from rest, right? Okay. That's not what's going on, right? You are not drop. That's why this one's in a balloon, right? Because a balloon would be a drop from rest, right? So yeah, skydiving was pretty fun. I didn't actually like the free fall very much. It was very violent. So you have the air is moving past your face at 120, 130 miles an hour. Your ears are popping constantly because we went from 14,000 feet to like 8,000 feet in 90 seconds, right? And so the pressure change in my head was hurting, like my sinuses were hurting, right? You couldn't hear it. All you heard was solid noise, right? You couldn't talk to anybody, right? And all the flappy bits on me were flapping, right? So it wasn't very pleasant in that free fall. Once the parachute opened, I was in heaven. I could have done that all day long, right? The glide, I love gliding, all that kind of stuff. But the opening of the parachute for me was actually pretty violent. My instructor, when we got down, said, yeah, it was violent for me too. I haven't had one. Apparently the chute had been packed weirdly, and when the chute came out, it hit my instructor on the back of his head. And then it kind of unfurled and then snapped open rather than sort of, they're supposed to come out kind of slowly and then open up, right? So he apologized. It wasn't his fault. But yeah, as an experience, I think I'd rather just bungee jump or something, which I haven't done yet.
For this equation I've made, wouldn't it, because of this equation, wouldn't it mean that if we opened the parachute early enough,
We would have negative? Yeah. That's assuming that these forces stay constant, which they don't. We're oversimplifying just a little bit. As to the question is why anybody would jump out of an airplane and open their parachute so low. I don't know if you can tell from that picture or not. That's one of our special services trainees. They're undergoing training for parachuting. Does anybody see what's attached to that service person's chest?
80 pounds worth of gear for also a dog.
It's a dog. This right here, there's the dog's leg. Okay, part of its tail. Here's the dog's body. There's the dog's face. Okay, here's the parachutist's arm around the dog, right? Oxygen mask. The dog can't see it, has oxygen mask. Okay? What is going on here? Like seriously, this diver, okay? It turns out special forces have dog units. I know this. My mother does training for seeing eye dogs for the blind. She trains up puppies, teaches the puppies how to be seeing eye dogs. And she knows a lot of trainers for like military dogs and all that kind of stuff. And I found out Special Services uses dogs in some of their operations, and they train the dogs to jump out of airplanes. Usually attached to their handler, sometimes not. I've seen videos of dogs, and it's funny, you can actually kind of see it there. There's a handle on the dog's harness, right? And they'll just pick the dog up by the handle and chuck it out of the back of the airplane, okay, with its parachute on and stuff like that, right? Dogs being smart won't do that on their own. It takes a human being to do something stupid like that. So the dog has a mask on, it's like blinders. So that it's got like an oxygen mask if they're jumping from a high point, right? And then they blind the dog's eyes, right? And then, check it out. It's easier though when they're attached, just so they can find each other. But the dogs are trained to find each other when they get down, okay? Find their handler, all that kind of stuff. It's really quite amazing. The reason I bring this up is because one of the jumps that they perform is called a halo jump. And halo stands for high altitude, low opening. It also means the thing you might be wearing if you do it wrong. And in this calculation, you notice how there was just a 6-meter difference in whether you hit the ground going too fast or hit the ground going at the right speed. Apparently, there's times when you want to be able to jump from a very high altitude, classified high altitude, down to below like the level of a mountain into a valley or below radar coverage or something like that. And so a human being's reaction time is not fast enough to be able to do that. And so they have to program the parachutes to do it for them. And the parachutes have a very precise window in which they have to open. And it's a very special kind of parachute. Of all of the injuries that our special forces units suffer that are not like combat related, that are more just like training and everyday walking around related, broken ankles and broken legs due to halo jumps is definitely the highest of all of them. So, yeah. Halo jumping, it's a thing. And kudos to our men and women that do that. Like, dang. Just dang. Let's do a quiz. Just put that one back on the test, Mr. Balogh, right? Why not? No, I never do that, okay? But in a sense, that question will be on the test. There is a question, is there not, a topic about conceptual, what was it, conservation of energy conceptual? Is that what I said is the topic? That was a conceptual conservation of energy equation. So yeah, that exact wording will not be on the test. But knowing energy and work and its relationship and all that kind of stuff. This one also may or may not be a true story, based on a true story. Okay, I'll let you decide which one I was in this story. We need, we need a picture, don't we? So there's a slope. What does a slope look like in physics? Hold on a second, my iPad decided to disconnect. I don't know why, but the first piece of software I used this morning decided it didn't want to work, and now this piece of software deciding it's not wanting to work. That's why it's not working. Not my fault. The Wi-Fi just pooped out. And now it just revitalized itself. Excuse me while I troubleshoot. Yeah, got it. Okay, this should work. Here it comes. And, all right, we're back. Sheesh. What do slopes look like in physics? Triangles. Okay, so there's our canonical hill. What do we know? We got a boy in wheelchair up here, right? And what's happening at the top here? It's moving, right? 1.4 meters per second. Okay. It's 2.6 meters high. So I'm interpreting that as being the vertical distance. Where does the 12.4 meters go? It's the hypotenuse, right? Sometimes you got to read, right, and not just assume. 12.4 meters long. Like, oh, that's 12. That's not 12.4 right there. Okay, the 12.4 is the length of the slope. Okay, and you're sitting there on the exam. You're not sure. Like now you're doubting yourself. You go, wait. Does he mean 12.4 horizontal or 12.4 along the slope? What do you do? Raise your hand. Come ask me something, right? Because that's the kind of thing I'd be like, no, it's the hypotenuse. I'm not testing you on can you decide if it's a hypotenuse, or I'm testing you to find out if you can do conservation of energy, right? So ask, just ask. Worst thing I can say is what? I won't answer that, right? It's the worst thing I can say. But I'll say it with a smile. What do we know about the bottom? 6.2 meters per second, right? The bottom of the slope is going 6.2. This 41 newtons, what does that look like? There's like a force here, right? Okay, of 41 newtons. And how do I know it acts up the slope? Right? It's air resistant. It's like a combination of air resistance and rolling resistance. In this problem, they've sort of put all the frictions together as a force, right? And since it's friction, we know it's got to act opposite the direction of motion, right? Okay. It seems like I know everything. What am I being asked to find? Find work. Wait. There's another force in this problem? Doesn't say that the boy in the wheelchair has gotten to the top of the thing and is moving and then just kind of goes, let's go of the wheels. Right? Whee! Okay, right? They're in a race, aren't they? Okay? They're in a race, so what is that wheelchair rider going to do? Boom, right? Right? He's going to grab those wheels and just really just put more effort in, right? So, there seems to me that like there's some sort of force, some sort of different program. Give me a second. There's going to be some kind of force, right, of the boy, like down the slope. But are they asking me to solve for the force of the wheelchair rider? No. What are they asking me to solve for? The work. A force times a distance? Watch this. Just the reason I'm giving you this problem is to show you something, right? What's our next step? Initial final zero. Okay. I hope it comes as no surprise that this is what I'm going to pick. Where I know something about where it starts. I know something about where it ends. I'm not sure where this work thing's going to come from, but I'm going to hope. I'm just going to try it. And worst case scenario, I've got to redo something, right? So work other plus energy initial equals energy final. Skip the work other for now. At the top of the slope, what kind of energy? Potential and kinetic. So mgh and 1/2 mv initial squared. Okay. Down at the bottom, final point. What kind of energy? Just kinetic. Why is the potential energy 0 down there? We put 0 there. So 1/2 mv final squared. Again, the question you're asking is it at 0? Yes or no? And then, is it moving? Yes or no? And then you write down the terms that are not 0. Okay, and then we have our work other, don't we? We've got two things that are doing work. What are the two things that are doing work? Work from the friction plus the work from the boy. Those are my two. That's my work other, right? Mm-hmm. F boy. Yeah, it's like the boy grabbing. He's like wheelchair. People in wheelchairs can push themselves, right? They can grab the wheels and, right? It's the interaction between their body and the wheelchair, right? And then, so we add up all those works. Now, we know what the work due to friction is, don't we? What is it? Negative 41 times 12.4. Why negative? It's going against the motion. Plus the work by the boy. So one thing I see students do, because you see it so often in the examples that we do and in the book and what I do, we break that work into a force times a distance. You only need to break the work up into force times distance if they're asking you about the force or the distance. What does this problem ask you to find? The work. Now, can you break it up, find the force and the distance, and then find? Sure, but you're doing too much work. Okay? Let work be work. If we're asking for the work of the boy, don't find the force of the boy and then multiply by 12.4. You can just, again, if you do it that way, you're not going to get it wrong. You're just going to do some extra math. Okay? So let's just leave that as work of boy. We know it's positive. How do we know it's positive? It's he's pushing down, right? The force is forward and the direction is forward. So we know it's going to come out as a number, right? But let's just leave it like that. So so this is the work done by the boy, plus mgh plus 1/2 m. Oh, I could probably put in numbers now, huh? You guys like numbers. Boy, okay, M47, 9.8, 2.6 plus 1/2 47 times initial speed, what was it, 1.4 squared, equals 1/2 times 47 times 6.2 squared. So look at this. That's a number, that's a number, that's a number, that's a number. What are all those numbers going to be? The work done by the boy. Right? We take this one over there, we take that one over there, we take this one over there, right? And then we solve for the work by the boy. We end up having our calculator lie to us several times, right? But now you know. Let me ask you, what do you know about numbers and your exam? You've been through an exam autopsy. What happens? What happens if you set this up completely right and then on this next step do it wrong? You're going to come to me during and let's assume I totally miss it while I'm grading your exam, right? And I mark it wrong, right? What are you going to do? You come to me and say what? I set it up right, Mr. Balogh. And then the numbers went wrong. Have I got your back on that? Yeah. Will your employer in an engineering firm have your back on that? No. Right? Okay. But I'm here to test your physics knowledge, right? Is it great to just get the number right and go on? Yes. That's the preferred output. But at the same time, I'm asking you to do a problem in 10 minutes. And you're stressed. And this stuff is hard. And you're new, right? And so that's why there needs to be communication back and forth, test autopsy, all that kind of stuff, right? So that you have a chance to say, hey, look, Mr. Balogh, I set this up right. That counts for something. And it does. It does. I do try to look for those things while I'm grading, but I do miss it. Okay. This turn, did anybody get it?
168.12.
That's what I got too. 168 joules. Okay. Had a friend growing up who in high school was in a car accident, lost the use of his legs, and we would do this. He had two wheelchairs. He had a wheelchair that was sort of like an everyday get-around wheelchair, and then he had a racing wheelchair that he would use to work out and to basically make us all look stupid on the track. Because we would be out there running a mile. And it's a bunch of us nerds, right, with inhalers, and we can't do anything. Running is something that, I don't like running at all. But we'd be trying to go out there. Did they still make everybody run the mile? You have to, do a certain time and all that kind of, okay. So that's what we were doing. And he is, lapping us on the track, right? Okay, just crazy fast. Oh my gosh. I remember that racing chair was so light. It wasn't made out of carbon fiber at that point, but man, it was lighter than his regular wheelchair. We always told him to use that one instead of his regular wheelchair. And he's like, no, the regular wheelchair is more comfortable. The racing chair is faster. So, yeah, he always used to, and we would ride on our skateboards and he would beat us. It was fun. We had a lot of fun. All right, where are we at? Do we have, one more time. One more time. Oh no, let's do a video instead. Let's do a video instead. This isn't a quiz, but we'll do a question answer kind of thing with it here, okay? First of all, does he look like he enjoys his job?
Absolutely.
No. I don't know if you know, I've played several of these videos. I don't know if you've noticed, but the people in them are not allowed to smile. Because this is science, right? And science is serious. Check this out.
Raising a mass increases its gravitational potential energy.
Do tell.
We'll use this triple track to show that this energy is conserved as it changes from one form to another. We'll release a rubber ball down each of these 3 tracks. Each track has a similar downhill section.
No smiling.
But the uphill sides have different slopes. If a ball is released from the top of each track, how high will it rise on the other side in each case?
So there's the question, right? We're releasing the ball along, and there's actually 3 tracks. It's kind of hard to see. 3 tracks, but they all end differently. How high does the ball go? Say it the other way around. Which track, the steepest one or not, whatever, which track has the ball go the highest? Okay? So turn to each other and try to figure out where the ball goes the highest. Which track? All right. Which track does the ball go the highest on?
Equal.
It's equal? Why would it be equal?
Potential energy is the same for each track.
Potential energy is energy, right? I mean, can the ball get more energy than it starts with? Only if it was pushing itself, right?
I thought on the steeper ones, like, they wouldn't go as high on this because gravity's
Because gravity seems to be like working more and all that kind of stuff, right? Which way does gravity point? Down. Does gravity care about slopes? Not really. Now, with acceleration, it changes a little bit, right? G sine theta, we learned, right? It's just not free fall. But the work that gravity does only cares about vertical displacement. Horizontal doesn't make any difference. So, what do I mean by that? No, it's kind of dark in here, sorry. I have my tennis ball, right? If I drop the tennis ball, gravity does some work, right? Okay, force is down, direction is down. If I take that ball and I do exactly the same vertical distance, but now I wave it back and forth as I go down, how much work did gravity do? More, less, or the same? It's the same. Gravity does not act sideways, right? It only acts down. And so it's what we call a conservative force. It votes, I guess, right wing in elections or something. No. Conservative forces are path independent. Work other, those are all non-conservative forces. Friction, somebody pushing their wheelchair, all these extra inputs, those are path dependent. Did my friend have to do more work if he did a different distance with his wheelchair? Yes. Okay? But gravity is a conservative force, meaning it doesn't care what the path is. It will always have the same amount of work. Generally, I don't talk about conservative, non-conservative forces in physics because it doesn't help all that much. But that work other is often called work non-conservative in other places. So anyway, that's why work other kind of exists. We're handling all the forces that where the length and the path that they take matter. So I don't know if that answered your question, Lewis, or not. Let's see what happens. Okay, if you smile, you're fired.
Here's the ball rolling down the first track.
Okay, thank you. All right, no smiling. All right, be careful. Oh, if you get this wrong, you're fired. Oh,
The second track.
oh. Uh-huh. Oh. Better not smile. No smiling. No smiling.
The third track. The ball rises to the same height from which it was released in each case.
Why was he being so careful? He didn't want to add any initial kinetic energy, right? Really wanted to get that ball to just sort of tip at the end, rather than if he gave it a little push, it would. If they gave it a push, would it go higher? Yeah, because it would have more total energy at the beginning. Have a fantastic rest of the day. I'll see you tomorrow for a lab, not lab. And if you don't know what that means, I'll post an announcement about it. Come tomorrow ready to do your homework.